Close enough. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So today I want to talk about, give you some examples of isomorphism and show you how we can calculate the matrix of a linear transformation on abstract vector spaces. So we're going to continue to think about linear transformations on abstract vector spaces and try to see what more we can say about them. So to start with, I just want to give you an example. So let's see here. Suppose T is a mapping from, let's say, P2R to R2 by 2, such that T of 1 is 1, 0, 0, 1. T of x is 3, 2, and then zeros like that. And T of x squared is 0. All right? So this is all I'm telling you. If T is linear, find its formula. Can you do it? So this is an example of the theorem that I'm about to prove for you, which is that if we have a function which is defined on a basis for a vector space, all right, then there's a unique linear extension of that function to the whole vector space that makes the function a linear function. So why is that? Well, what's a typical thing in P2R? I heard ax squared plus bx plus c. I'll buy that. And of course, if we assume t is linear, we can say, well, that's a times t of x squared, right? Plus b times t of x, yeah? Plus c times t of 1. So you see, if you're given what the values of the mapping are on the basis, that suffices to define the rule on the whole of the vector space. And the rule in particular is what? So we've got thank you. Oopsie. I got my things out of order, didn't I? Let's see here. So that's, we got 3b plus c, 0, 0, and 2b plus c. And there you go. That's the formula for the linear transformation. You see, knowledge of the value of the function on the basis was enough to define it everywhere. Hey, while we're at it, let's calculate the kernel and the range of this example. What's the kernel of t? Sure. So kernel t would be f of x in P2, right? Such that t of f of x equal to 0. In other words, it's matrices of the, not matrices, it's ax squared plus bx plus c such that what? This is in the kernel. if what? 3b plus c 0, 0, 2b plus c is equal to 0, right? So what is this? This gives us two equations, right? It gives us 3b plus c equal to 0 and 2b plus c equals to 0. Right? And hey, those are two lines in BC space which don't have the same slope. So the only place they intersect is at the origin. I mean, this equation, you can solve this two equations and two unknowns. This has solution b equals c equals 0. You could solve both for c. You'd get 2b equals to 2b equals to 3b. So b is 0. Once you know b is 0, c is 0, okay? Wait a minute, where's a? A is not 0. X squared is also not 0. No, I said that a is not 0. A is what? A is a free variable, right? So this shows that thus, the kernel of T is in fact just the span of x squared. Because something in the kernel has the form ax squared. What's the range of T? I can see that the range of T is the span of 1, 0, 0, 1 and 3, 0, 0, 2. Either by logic or by the formula in purple to the left here. Those are the possible outputs. All right? There you go. So theorem, if L is a mapping from beta to W, where beta equal to, say, V1, V2, Vn is a basis for V over F, then there exists a unique linear function T from V to W such that T restricted to beta is equal to L. So what's this restriction business? What's that mean? What's a restriction? If we have, f as a function, let's say from a to b for a second, and say a1 is a subset of a, then f restricted to a1 is by definition a mapping from a1 to b, where f restricted to a1 of x is just equal to f of x for all x in a1. We also say f is an extension of the restriction. Right, so this is just, it may or may not have been covered in Math 200, depends. So you said surjective and injective was not covered in 200 last semester?
I didn't hear those words ever.
No?
No, not even Webster's dictionary.
Not even Webster's dictionary. Well, these are standard.
I can read, but still.
These are standard math terms, and if we have, it is in my chapter 1 in my defense. Like if you're reading the notes, you should have come across these in the reading already. But I understand last semester was the mysterious 13-week fall semester which means that there was an arbitrary week cut off all of your classes, right?
So you're
So
saying I got one less week with Dr. Joseph?
I'm saying that you should have gotten a discount. You should have only had to pay 13/14 of the usual tuition last semester. That's what I'm saying, yes. Did that happen?
Yep.
No. So you see, you guys should have revolted. You guys should have objected, you know? What can I tell you? And yet this semester well, anyway. I'll shut up. There's some, anyway, I can't talk about this. All right, so listen, the concept of restriction and extension, it's been with you since pre-calculus, right? Like this comes up, we talk about inverse sine. Is inverse sine the inverse for the sine function? How about sine? F of x equals sine x, just, let me just digress here for a second. Does this have an inverse? Well, if you take the natural domain to be all reals, not only does it fail the horizontal line test, it fails it rather epically, right? I mean, like, you pick a horizontal line that intersects the range, you've got not one, not two, infinitely many points of intersection, right? So how can we talk about inverse sine? Right, inverse arc sine, as it's also called. Inverse sine is actually sine restricted to minus pi over 2 to pi over 2 inverse. The inverse sine is actually the inverse of the restriction of sine to that particular domain. Because if we just focus our attention, if you narrow your attention to minus pi over 2 to pi over 2, right there, right, then that red line there passes the horizontal line test. There's, each output's only hit once, right? It's injective, so you can invert it. That inverse is the arc sine. So that already involves the concept of restriction and extension, right? Okay. And here, my first example, I gave you the value of a map. To make this better, I should have really said, I just use T in both things, but I'm saying you could define here L. I could make these L, and then L would be a function from the basis 1x squared, right, to R2 by 2. Just to make the transference between my example and the theorem more complete, yeah? Okay, fine, whatever. What's the proof? Let x be an element of V, then x is equal to the sum. I equals 1 to n of, let's say, Ci Vi, right? Because if beta is a basis, we can build any vector in V as a linear combination of, right? And this is for what? For unique C1, C2, Cn, we call these what? Coordinates, right? These are the coordinates of x with respect to beta. Right? That's what the C1, C2, Cn is. We've talked about these before. So define T of x equal to the sum I equals 1 to n of Ci L of Vi. So here we assume L from beta to W is given, right? Which means that L of Vi is defined, right? Just like L of 1 and x squared was given in my first example. So we know the values of the function on the basis. Here they are. This is what? This is an element of W, right? We're taking a linear combinations of things in W, which is again where? So this is, clearly in W. So that's point number 1. At least this is defining a mapping going from V. How do I know that's single valued? Why is it single valued, this formula? The C's are unique, right? They're coordinates for the vector. L of Vi is unique because we're assuming L is a function, so it's a single value. So that is a linear combination of things which are, just single values. So it's again a single value. So this is a function. Does it restrict to L? You can check. This restricts to L. If I just look at what is T of like T of Vi would be what? Let me use J. Curses. Yeah. So what is Vj? Vj is equal to the sum I equals 1 to n of Kronecker delta ij Vi. In other words, Ci is Kronecker delta ij here. The coordinates of the jth coordinate vector they're just 0 when you're not in the jth spot, and they're 1 when you're in the jth spot. Which is so I put that here. What happens if we take the sum I equals 1 to n of Kronecker delta ij L of Vi? Here J is fixed, but J is fixed and we're doing a sum over I, right? What happens? Kronecker delta is only non-zero when I is equal to J, which means this finite sum just reduces back to what? Just the J case, right? I mean, only J survives. We just get L of Vj. And what's that show? That shows you that if you feed T anything in the basis beta, what do you get? You get L of that thing. This proves that T is an extension of L because they agree where L is defined. What's left to show? Why is this unique? Well, it's unique by its construction because the coordinate is unique, right? And the L of V1 and V2 and L of V3, this is unique. It's given to be a function. So the formula which I wrote down proves uniqueness. Can we prove that it's linear? How would you prove this is linear? Right? Right, so we would just look at T of like x plus, say, C is probably a bad choice, C x by, x plus by. And then if you look at the coordinates for that and work through the definition, you'll get that that's T of x plus b times T of y. Precisely because the coordinates of x plus by are the coordinates of x plus b times the coordinates of y. And that formula together with this gives you the linearity. So this is important because this means that if we want to define a linear transformation, how can we do it? We don't even have to give the formula for all possible values. It suffices to define a linear transformation on the basis. If you tell me how the linear transformation is working on a basis for the vector space, that says what it does everywhere else. This is really surprising. Let me try to shock you a little bit with how weird this result is. So suppose you're graphing a function, right? Y equals f of x. And a person tells you 1 point on the graph other than the origin. Does that suffice to tell you what the function is? It doesn't. But in the case of a linear function, that uniquely defines the linear function. Its graph is this, right? In other words, it's mx. Like picking that one point, AB, m equals to b over a, that one point is all it takes to fix a line through the origin. As long as that point's not the origin. In 3 dimensions, if you give me 2 points, they can't be collinear with the origin. Okay? So they can't be on the same line from the origin. But if you give me 2 points, which are like that, that uniquely defines z as a function, a linear function of x and y. Because there's only one plane that also goes to the origin like that, right? Which has this triangle and then everything past it. So here I'm supposing f, I'm trying to say f is going from R2 to R2 linear. If I tell you f is going from R2 to R2 and it's a linear map, telling you 2 points which are not the origin, that suffices to define the map by this theorem. Right? If this point, all right, well, I'm going to, enough. This is an important theorem. All right, so moving along here. I need to show you some examples of isomorphism. I think I'm going to erase this here. Let's see here. Suppose I have V is equal to R4 and W is equal to C2. My claim, these are isomorphic as real vector spaces. Can you tell me what the isomorphism is? Psi of A, B, C, D equals what? Make them real and imaginary. So you're saying like A plus BI, C plus DI. Indeed. You can check. You can prove that this is a linear map over the reals. It's surjective. It's injective. In fact, you could easily write down the inverse to this map, right? So it's a linear bijection, which means that that's an isomorphism. So this shows that, of course, this supports my claim that R4 is isomorphic to C2 as real vector spaces. Let's do something weirder. How about V equals to R2 by 2 and W equals to P3R? Again, my claim is that these are isomorphic as real vector spaces. So one way to construct an so these are simple enough that we can usually write down the formula just by some thinking. But there's another technique we could use as a sort of general guideline for when you're lost and you don't have an insight into the formula. Like maybe you're there right now. Maybe you don't have an insight to the formula I'm about to write down. One general technique we can use to construct isomorphisms is two vector spaces over a field are only going to be isomorphic if they have the same dimension. All right? So one way you can create the isomorphism is take the basis for your first space and simply map it to the basis to the second space, and then use linear extension to define the rest of the map. That will be an isomorphism. So if I can use that principle here. Like, what's a basis for R2 by 2? The lexicographic, remember? It's E11, E12, E21, E22. That's a basis for V. What's a basis for W? How about 1x, x squared, x cubed? That's the standard monomial basis for cubic, possibly degenerate polynomials. And so if you define a mapping by simply transferring one basis to the other and then extending linearly, that's an isomorphism. Why is it an isomorphism? So I'm going to say, let psi do this, then extend psi linearly. You're like, I'd rather write a formula. Fine, me too, in this case. I'd rather write a formula. The formula is easy enough to write here, right? Because the formula is just this. A, B, C, D maps to, a plus bx plus cx squared plus dx cubed. There you go. This is a surjective, this is a bijection which is linear. It is an isomorphism between 2 by 2 real matrices and cubic polynomials. Any questions? Yeah.
Is it just simply a matter of translating into the vector space that's transformation goes into, or are you just leaving the matters of subjective and objective for us to do for the problem?
Well, there's a theorem, right? And one of the theorems that we know is that let's see here. There may be a theorem which cuts the work down, but it's fairly obvious that this is surjective. Why is this surjective? By construction, let me give all of these a name. Let's call these gamma. Let's call the set of all these in that order beta. So it's basis beta, basis gamma, all right? So by construction, gamma is a subset of the image of psi, right? But gamma is a basis for W. And the range is a subspace, right? So it's closed under spans. So the span of gamma is also a subspace of the image, but the span of gamma is all of W. So that proves that it's onto. So the fact that we're mapping to a basis gives us that it's surjective, right? Because we're hitting the basis non-trivially. Unlike my initial example, right, where this was not an isomorphism. And why is it injective? I know. What I should do is I should go back and look at that laundry list of theorems we had about linear transformations and try to see if there's not one in there somewhere that I could use to argue why psi so constructed was one-to-one. Yeah? I know it is. I'm quite certain of this. This is a theorem you could prove, which is that if you map if you define a function by linearly extending, mapping one basis to another, it will necessarily be the case that such a map is an isomorphism. It has to be both one-to-one and onto. I mean, the inverse map is very easy to write down here, right? Like, what's the inverse map? Psi inverse of a plus bx plus cx squared plus dx cubed is equal to abcd, right? And so if you can construct the inverse map, it's pretty easy to prove one-to-one, isn't it? Like, suppose you can construct the inverse map, generally speaking. If you have, if I have psi of v equal to psi of w, and I know that psi inverse exists, I just take psi inverse of both sides, right? What's that tell me? So if I suppose that I have psi of v equal to psi of w, if I just take psi inverse of both sides, I get that v is equal to w for arbitrary v and w, which proves that the mapping is one-to-one, right? Equal outputs must imply equal inputs. So that essentially is the proof that this construction will always, the fact that we're mapping to a basis will always give us surjectivity. The fact that the mapping is also obviously invertible easily gives you injectivity. Okay? Now, but I think my examples so far are misleading in the sense that it's not always so easy. Okay, like it could be something a little bit like yuckier. For example, something like let T be the mapping from P2R to P2R given by T of f of x equal to, say, I don't know, f of 0. Sure, that'll do it. Find isomorphism from kernel of T to Rn for appropriate n. See, now this problem, I can't just rattle off the formula here, right? I've got something I've got to digest, I've got to work out in order to get to the point of writing the formula here, right? Let's work through it. Let's do it. So we're looking at T of ax squared plus bx plus c is by definition what here? F of 0, right? Which is what? Oh, you know what? This is still too easy. Let me take, if you have some mind, I want to make this just slightly uglier. Instead of putting f of 0 there, let me put f of 1. Because then this will give us a plus b plus c. So what's the kernel then? What's the kernel? Can I tell you something about kernel? Whenever I think of kernel, I think of the classic Monty Python sketch about the mafia going to the military guys and threatening them. It's a nice base, Colonel. A lot of tanks you got out there, Colonel. But this, of course, is not the same Colonel. But that's what I always think of. I don't know. I love the idea of the mafia, threatening the military. It's awesome. Okay, so the kernel here is what? It is ax squared plus bx plus c such that a plus b plus c is equal to 0. Right? So with that in mind, I say that we let c, well, I mean, you pick it. Which one do you want to keep? A, B, or C? Get rid of A, you mean? Solve for A? Whatever I want. Doesn't matter what you want. Let's see here. Minus b minus c x squared plus
Is that what marriage is like?
bx plus is that what marriage is like? Huh. My wife does not watch these videos, I think. I think I missed something. Ah! Let's see here. So I want to group things. I've got b times x. 1 minus x squared.
Don't worry, I've got your back.
You've got my back. All right, yes. Huh. It's good that you have my back. And you're not interested in any kind of personal gain. It's just purely of your own volition. It's good. It's good. So this is the span of x minus x squared and 1 minus x squared, yeah? Forget that. My point is it's now clear to me that the basis for the kernel is x minus x squared and 1 minus x squared, yes?
Of course.
Are those, how do I know that's a basis? Well, I mean, that's just, they span, I just calculated that. Are they linearly independent? These are definitely linearly independent because I cannot write one as a multiple of the other, all right? Consequently, what's the isomorphism? How about this? Psi of a times x minus x squared plus b times 1 minus x squared equal to ab. There you go. That's an isomorphism, n equals 2. Not only is it an isomorphism, what else is it? It's an endomorphism? No, no. This psi I just wrote here, right? I'll tell you this. For basis, beta equal to x minus x squared, 1 minus x squared, psi is the coordinate map with respect to the beta basis for the kernel. This is a coordinate map from the kernel of T to R2. In other words, I just used the coordinate map to form an isomorphism here. And this is one way. This is also, here's another way of constructing isomorphisms. All right. I've got V, all right, with basis beta. Over here, I've got W, basis gamma. And if I want, I can construct an isomorphism up here psi in a particular way. So here's how I do it. I take my coordinate map, phi beta. That maps me down here to f, fn. So here I'm going to assume the dimension of V is equal to the dimension of W, and it's equal to n. So if the dimension of the vector space is n over f, that means that there's a coordinate map going from the vector space down to fn, and this coordinate map's a bijection. There's also a coordinate map over here, like so, to fn, the gamma coordinate map. All right? And so if I want to construct an isomorphism from V to W, one of the ways I could do it is just to use my coordinate maps. See? How can I go from here to here? I mean, these are, I mean, I can take the identity map down here if I want. So what should I make psi? Let me maybe make the path in red here. Wait a minute. Oops. Oopsie, oopsie. I wanted to go like this. Whee! So that means I should make psi equal to the last shall be first. So phi gamma inverse composed with phi beta. See what this does? Because these are really the same. I mean, I could have just drawn one Fn in the middle, you know? So what this does is it takes a point up here, right? It maps it down to its coordinate vector here, which you could just as well view over here. And then phi gamma inverse takes that coordinate vector and converts it into an abstract vector in W, which corresponds to the initial vector in V. This is the composition of linear maps and is therefore linear. And it's also the composition of bijections, which is therefore a bijection. In other words, psi is an isomorphism from V to W. I don't usually use this to construct actual formulas for examples like my example 1, 2, 3 because it's just not the right way to think, right? But this kind of diagram is actually really important to organize your thinking in here, all right? Especially for the next topic on our agenda, which is to find, to generalize the concept of a matrix of a linear transformation to the abstract context. So let me make a definition for you guys, all right? So suppose we've got a linear transformation going from vector space V to vector space W, and I'm going to draw a picture. So here's V, and it has basis beta. We've got this linear transformation T, goes over here to another vector space W with basis gamma. All right, so here, let's suppose that V is the span over some field F of beta. And let's let beta equal to V1, V2, Vn. All right? So that means that there is a coordinate map, the beta coordinate map down here to Fn. Yeah, fine. On the other hand, it also means that there's a coordinate map over here down to Fm. Here I'm supposing the dimension of W is equal to M. All right? We can trade the given abstract linear transformation for a corresponding transformation on column vectors if we filter through the given coordinate maps. All right? So essentially, by definition, this picture essentially defines what I'm about to write down here, L sub T beta gamma. So this here, the notation is L sub A of x, right, is just equal to AX as usual. In other words, L sub A has standard matrix of L sub A equal to So when I say L sub A, I'm just talking about multiplication on the left by matrix A. It's the left multiplication by A map. What's the standard matrix of L sub A? Your choices are 0, 1, or A. A. Have the courage to choose A. Yes, A is the standard matrix of L sub A. So I'm trying to say this picture essentially defines the matrix T beta gamma. Now there's an alternative definition I could give you. Here's the definition. The matrix, non-standard matrix of T with respect to the beta gamma basis, it's by definition the following matrix. The first column are the gamma coordinates of T of V1. The second column is the gamma coordinates of T of V2. And so forth and so on. Eventually you get to the gamma coordinates of the nth thing in the beta basis. So this is the matrix of a linear transformation with respect to a abstract pair of bases. Can you tell me how T is related to the L sub T beta gamma? How is this T related to all this? I mean, we could do like this, right? Like that. And so that would show me that L of T beta gamma is equal to, so the last shall be first. The thing that, so this, I start here, I go across here, I come back down here. So I do that one, the last is first. So phi gamma, silence, composed with T. Shush. Shut your face. What's that? I am not an Avenger. Hey, well, that's what an Avenger would say. They're not really so clandestine, are they? I mean, I don't know. I mean, modulo Spider-Man. Oh, he's dead. Let's see here. Oh, I'm sorry. Spoiler alert. Let's see here.
If you haven't watched it by now, I mean,
Yeah, if you haven't watched it by now, it's on you. Fair enough. I guess you could ask the question, dead in which movie, right? I mean, there's so many movies. So specifically, I'm talking about when he dies at the end of Avengers Infinity War, where Thanos clicks his fingers and, you know, half of the people vanish. You know, the half of the people who have future franchises, which means that they're going to be resurrected in the next movie, right?
Yeah.
So everyone who's currently
Trailers to Spider-Man Homecoming.
right, everyone who's currently alive shall be dead after the next Avengers Infinity War movie, right? And everyone who's dead will be alive going forward for the purpose of sequels like Black Panther 5.
It's called Infinity War because their lives never end.
It's called Infinity War because their lives never end. Interesting. Okay, I feel like I've digressed slightly here. But this, guys, is a stone-cold formula that relates the abstract matrix for the linear transformation T to the coordinate maps. So let me give you an example, and then we'll be done for today. If I go, say, from, let's pick something relatively simple, like R2 by 2, right? And so I take a matrix here, let's say A, B, C, D, right? And where do you guys want to go to? You pick it. What do you want? What do you want what do you want W to be? Where do you want me to go? 5?
Sure.
You know what I'm going to do? I'm going to go to R2 by 2 again because it's more fun that way. And it's going to be A transpose is the map. So T, that's T of A. So T of A is A, C, B, D, right? So I'll use the, oh man, I erased it, but the lexicographic coordinates that we talked about earlier today. Yeah, the E11. So I'm going to actually let that be, and that will also be over here. So I'm going to take gamma equal to beta, all right? So if you look at that, the coordinate vector of A with respect to the beta basis is what? A, B, C, D. All right. Over here, the coordinate vector of T of A with respect to the gamma basis, which here is beta, is what? AC, ACBD. And to go from here to here, you want to multiply by, in this case, T beta beta. That's what this, yet another way to look at this would be this T beta gamma multiplying by V beta is T of V gamma. So what that says is if you calculate the coordinate vector of something in the domain and you calculate the coordinate vector of its image, the matrix, the abstract matrix, is whatever it takes to get from there to there.
Should that be beta gamma or not beta?
Beta equal to gamma.
That might-
Yeah, that's fine. So in this case, sorry, I should have more time. Something distracted me. Let's see here. We have 1, 0, 0, 0. 0, 0, 1, 0. 0, 1, 0, 0. And 0, 0, 0, 1. Because that matrix multiplied by ABCD gives me ACBD. But you can also check that the columns in that satisfy my definition, right? Like what's T of V1? T of E11 is what? Is E11, right? Which is the first thing in the basis, which is why we have coordinate vector 1, 0, 0, 0 for column 1, and so forth. Anyway, I will try to do more examples for you next time. Thanks, guys. Oh, Tristan, you exist. Haha. I keep picking wrong days to hand those back to you.
Thank you.
Uh-huh.
Yeah, just